Hey everybody, this is the lecture on section 4.4. On coordinate systems. So, if B, which is this set of vectors, B1 to Bn, is a basis for vector space V, then B spans V. So, for every little vector v in V, there's a linear combination x1 v1 plus xn vn, or not v1, b1 bn equal to v. Furthermore, it spans, basis means it spans the vector space. Basis for that vector space means two things. One, it spans. Two, it's linearly independent. So spans means any vector in the vector space is a linear combination of those guys. So here's a linear combination. And when it's a basis, what's good about the basis is that its linear combination is unique. The linear combination is unique. That is, if you have another linear combination is also equal to V, then you can subtracting subtract this from this, you have that x1 minus y1 b1 plus xn minus yn bn is equal to, well, this minus this, v minus v, which is 0. Okay, but because it's linearly independent, each of these coefficients is 0. B equal to b1 to bn is linearly independent. We must have that x1 minus y1 equals xn minus yn are all 0. Right, so the linear combination is the same. This linear combination coefficients y is the same as a linear combination with these coefficients x, because these guys are all 0. Because it's linearly independent, right? The only solution to that system of equations is the trivial one. All right. So definition. So that's what's great about bases, right? A basis for a vector space, it spans it. So every vector is a linear combination of the basis vectors, and that linear combination is unique because the basis is linearly independent. If it wasn't linearly independent, it wouldn't be unique. Okay, so it's got those two nice properties, and from those properties we get the following. We make the following definition. If B is a basis for vector space V, then we define the coordinates is a basis for vector space V, and little vector v is in vector space V, then we define the coordinates of little v with respect to basis B as the unique vector in Rn of coefficients x1 to xn, where those are the coefficients of the linear combination of the basis vectors equal to v. Right? So given a basis for a vector space V, the vector little v in that vector space can be thought of as a vector in Rn. So remember what I was saying before, is that every vector space is really just Rn in disguise. And this is basically it. Right? Because once you pick a basis, then you've got it as a vector in Rn. In any vector in Rn. And we'll talk more about that as we go along here. And then this vector is denoted like this, bracket V, the subscript B is this vector x1 to xn. So rather than writing this thing every time, you sometimes use this notation. Okay. All right. So, for example, all right, consider the elementary basis. Remember the elementary basis? B equal to, and it's 1, 0, 0, 0, 0, 0, 1, 0. Zero, zero, one, zero, 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 0, 1. All right, consider the elementary basis for vector space Rn. Well, now for any v in Rn, right, the coordinates of v with respect to the elementary basis is just v itself, right? For example, like 3, 1, 2, as a linear combination of the elementary basis is just 3 times the first vector plus 1 times the second vector. Let me put a minus 1 there. 0, 1, 0. Plus 2 times the last vector. Right, so 3, negative 1, 2. Right? So 3 minus 1, 2. B is just 3 minus 1, 2. So, that's for the elementary basis, but I mean, if you change the basis, it becomes a little bit more interesting. Consider basis, following basis for R3. We'll start with 1, 0, 0, and then we'll go to this vector, 1, 1, 0, and then 1, 1, 1. So that's also a basis for R3. Find, so let's say 3, 1, minus 2 with the coordinates of 3, 1, minus 2 with respect to b. So we need to find the linear combination of these vectors that's equal to that. Right, so that is find x1, x2, x3 such that, so let's write out that whole thing. x1 times 1, 0, 0 plus x2 times 1, 1, 0 plus x3 times 1, 1, 1 equals 3, 1, minus 2. That is 1, 1, 1, 0, 1, 1, 0, 0, 1 times x1, x2, x3 equals 3, 1, minus 2. Right? That is, row reduce this system. 1, 1, 1, 0, 1, 1, 0, 0, 1, 3, 1, minus 2. So it's already in row echelon form. You just need to put it in reduced row echelon form. So subtract row 3 from row 1 and row 2. So I got 1, 1, 0, 5, 0, 1, 0, 3, 0, 0, 1, minus 2. Subtract row 2 from row 1. 1, 0, 0. 5 minus 3 is 2. 0, 1, 0, 3, 0, 0, 1, minus 2. So there it is. So x1 is equal to 2, x2 is 3, x3 is minus 2. Right? So notationally we write that the coordinates of 3, 1, minus 2 with respect to this basis b, right, is equal to 3 minus 2. Right, so with a different basis, you get different coordinates. All right? And when you have a basis, you'll always get a unique solution, like we were talking about here. This system of linear equations will be consistent, right? Because those vectors, they span the whole vector space, and the solution will be unique because the vectors are linearly independent. So you're always guaranteed to get that when you start with the basis. Okay, so the coordinates of 3, 1, minus 2 with respect to this basis, b, where is it? 1, 0, 0, 1, 1, 0, 1, 1, 1, is 2, 3, minus 2. Okay? So finally, I'm going to just mention the theorem. I'm not going to actually prove it. It's intuitively, it's quite obvious, actually, from everything we've just been saying. But the theorem is as follows. Let V be a vector space with basis B of n vectors. The function t from V to Rn given by t of V is equal to the coordinates of V with respect to basis B is a linear transformation. That is 1-to-1 and onto. In other words, so I'm going to use a word you really haven't heard yet, V is isomorphic. Isomorphic sort of meaning the same as. It's the same as in a very specific technical sense. Is isomorphic to Rn. In other words, that's the disguise. That's a disguise for V masquerading as R. That's a disguise for Rn masquerading as V. Okay, so that's really what is meant by this. Now, not every vector space has a finite basis like this. Some vector spaces need infinite bases. When you talk about the set of all continuous functions of the real numbers, I mean, that does not have a finite basis. It has an infinite basis. Actually, it's got a infinitely uncountable basis, as they say. So you can't really. Well, no, it's a countable basis. What's a countable basis? Anyway, you can't make it Rn. I mean, there's a way to make it R infinity, but that's not necessarily the greatest way to think about things. So anyway, this is basically what it is. So really, every vector space is Rn in a certain sense for some n, whatever size your basis is. Okay, that's the lecture for this section.